it sounds like a Black Mirror thing. Absolutely. Yeah, look at those kids. They're not talking. Welcome back, everybody. Let's talk about nomenclature some more. I think, where do we leave off? We were talking about the names and formulas of monatomic ions. And so what we need to do is we need to be able to take those monatomic ions, put them together, and form ionic compounds. Then after that, we're going to move on to polyatomic ions. That's the same idea, species that have charges but have more than one atom, polyatomic. So we're going to go from that point and see what's going on. Then what we're going to do is we're going to take those polyatomic ions and we're going to make ionic compounds with them. So that's going to work the same way as you do it with monatomic ion. It's just going to be a little bit more formula writing involved. And then we're going to start to move forward with some of the different stuff with the rest of the chapter and nomenclature. So let's go ahead and get started when it comes to ionic compounds. Okay, so we've already talked about what happens if you have sodium and it loses an electron and becomes sodium ion. We talked about what happens if you have chlorine, in this case chlorine atom, and it gains an electron to become chloride ion. We talked about how we name the ion, and we talked about how you predict the charge of the ion based on the position of its parent atom in the periodic table of elements. Group 1 will form group 1 ions, group 17 will form, group 1 will form +1 ions, group 17 will form -1 ions, etc. So we want to take a look at what we're going to do, though, is what happens when a positive ion and a negative ion get together to form a compound. These are called ionic compounds. We haven't talked about bonding, and so I won't go into much about it at this point, but these are held together by actual charges. Positive is attracted to negative, and these bonds happen to be pretty strong. And so ionic compounds tend to be solids at room temperature, and they tend to have really high boiling points. Now, what we want to be able to do is take a compound and name it. You might know from other classes that this is sodium chloride. And so let's examine how I put together this name. What's the name of this thing? This is sodium ion. Remember, the name includes ion. Remember that for negative monatomic ions, we use the atom's root, in other words, the atom's parent name, and then we take off the suffix and we replace it with "ide." So instead of chlorine, we have chloride. And so IDE always refers to monatomic anions. So if you hear "ide," it's referring to a monatomic anion. And so that's why if you see phosphide, then you know that is the monatomic anion from phosphorus. The only challenge that you have now is figuring out what the charge is. And because phosphide is in group 15, and group 15 forms 3- ions, that's the charge that you'll assign to it. So this is phosphide. Okay, so let's go back to the naming bit. How did I decide that the name of this compound was sodium chloride? Well, it's really straightforward. You use the cation name without ion, because the word ion is included in all cation names. And you put together that with the anion name. And this is essentially, at the end of the day, this is how you name ionic compounds. It's that simple. You put together the cation name and the anion name, and you take away ion from the cation name. It's that straightforward. So if you have a compound that's made with even something a little bit more complicated, like let's think about Fe2 plus. Let's do Fe3 plus. Remember how we call this. This is a transition metal, and transition metals can take on multiple charges. And so we have to use Roman numerals in the name. This one is called oxide. So how do I put together the name of the compound? So I'm going to leave that up there because I want to make sure we see. It's just the cation name without ion and the anion name. So it will be iron 3 oxide. Now, one thing that I haven't done for iron 3 oxide is I haven't written down the formula yet. And the formula is not difficult, but it's not trivial either. In the case of sodium chloride, the formula was NaCl. What I'd ask you to remember is that an ionic compound is made from ions. It is made from something that has got a positive charge and something that has a negative charge. So the particles really do have charges, and they don't go away when they make ionic compounds. The charges, in fact, are what holds it together. But the compound itself is overall, it's got a neutral charge overall. The compound overall is neutral. And so this is important because in the case of sodium chloride, you have a 1 plus cation and a 1 minus anion. So you only need one of each in order to cancel the charge out, right? So plus 1 plus minus 1 equals 0. Cation, anion charge. And together, the cation and anion charge equals 0. This is a little bit more straightforward if we look at something like, we'll come back to iron 3 oxide here in a second. What if we do calcium fluoride? And I should be careful because it doesn't actually have a capital letter there. It's all lowercase. So what about calcium fluoride? Now remember, it's still up here in the corner. It's the cation name without the word ion and the anion name. Well, fluoride, we look on the periodic table. It's group 17, so it's F minus. The same thing with calcium ion. We look on the periodic table, it's Ca2 plus. So if the charge of the ionic compound, calcium fluoride, is going to have an overall neutral charge, then how many fluorides do you need as compared to how many calcium ions you need? Well, the calcium ion has a 2+ charge. So you need more fluoride to balance that out. You need how many more? You need 2, right? Yeah. Oh, thanks. Diana's helping me with my spelling, which is wrong. And that's going to be often because I forget this one. Fluoride. Fluoride. So I digress. How many fluorides do you need to balance out the positive 2 charge or in the calcium ion? You need 2 of them. So the formula for calcium fluoride is CaF2. You need 2 fluorides to get to a net charge of 0. Well, let's go back to iron 3 oxide again. How does that work? What I'm going to do is I'm just going to rewrite the formulas and the name. So this is iron 3 oxide here. I know that it comes from an iron 3+ ion and an oxide ion, O2-. How many of these do I need in order to get a neutral charge overall? This one's a little bit more of a challenge, if you think about it. What I want to think about is, I'm going to show you a trick in a second, but I want to get back to basic principles first. And if you think about it, the least common multiple of 3 and 2 is 6. And so how do we get to 6? So 3 times 2 equals 6. And so how many Fe's would I need in order to multiply times 3 to get to 6? I need 2 of them. How many oxides would I need in order to multiply in order to get 6? I'd need 3. And so let's think about what the overall charges are. I have 2 ions that have a 3+ charge. This means that I have a total of, in the positive charges, of 6+. I have 3 ions that have a 2- charge. So the total that I have is 6- from the anions. And if I add them together, the net is 0. Okay, now every chemistry instructor on the planet teaches the following trick. If you look at what's going on, we can do something called cross down. And what I mean by cross down is that I can take the charge on one ion and cross it down to be the subscript on the other ion. So do you see how the charge on calcium becomes the subscript on fluoride for calcium fluoride? And vice versa. Do you see how the charge on fluoride becomes the subscript for calcium? We don't write the subscript 1, so it's understood to be there as 1. Let's see if that worked out for iron 3 oxide. Did the cross down work for that? Yeah. So the question is, why can't we just add -1 to oxygen? And I'm not exactly sure where we're heading with that question. But remember that ions form particular charges, unless it's a transition metal. But even if it's a transition metal or a post-transition metal like lead, it's not going to take any charge you want. So if I tell you it's oxide, then that means it's O2 minus, and it can never be anything other than O2 minus. So you can't just say, well, okay, I'll just make it O3 minus then, and things are easy, right? Because that's not the formula for oxide. Oxide is a specific ion that has a specific charge, and its charge is -2. The same thing for iron 3 ion. It's the iron ion that forms at a charge rate of +3. And so you can't change that. I want to make sure, hopefully that sort of addresses that question. We can't just change the formulas of ions to suit our needs, because then we really have changed the identity of the species. All right, so we can do this cross down, and it works essentially every time. And so let's take a look at something like lead 2 nitride. Well, how does this work out? Well, the lead 2 ion is Pb 2+, and nitride is the ion that forms from nitrogen. We look at nitrogen in the periodic table and we see that it's in group 15. And so group 15 forms 3- ions. So that's how we know the formula for nitride. And if I were going to do a cross down to get the formulas, I would be able to write the formula for lead 2 nitride as Pb3 N2. I want to pause real quick and see if there's any questions about how to do this. Okay, so at the end of the day, remember that the heart of this, you don't know. So the question is, how do we know that lead 2 is 2? You won't know what the charge of lead 2 is, lead 2 ion is, unless the reader tells you, because lead is one of those post-transition metal atoms, and it's not predictable. It's not predictable like sodium and potassium and lithium and calcium and magnesium. It's not predictable like nitride and chloride and oxide and sulfide. So what you have to do is the reader has to give you some information, or the author has to give you some information. And we'll do that every time. There's ways that I can get you information, and I'm going to give you an example in reverse in just a second. But the one common way is to just give you the name, and that's how we've been starting. In this place, we've been taking names and turning them into formulas. But let's do an example where I take a formula and turn it into a name. How about this? What's the name of this compound? Right, and so Diana, this is what I'm sort of addressing. The information for lead 2 and chromium and transition metals and post-transition metals will be given in some fashion. I will never just say, write the formula for the chromium ion, because chromium is a transition metal. It takes different charges. There's going to be 4 exceptions, and I'm going to write the 4 exceptions down in just a second. There will be 4 transition metals that take the same charge all the time, and therefore you don't use Roman numerals for them. I'll write them down in a second. But chromium's not one of them. And so I can't just say, what's the charge of the chromium ion? Because you have to say, well, which one? All right? And so I'll have to give you some way to decide. If I give you the name, then that's really easy. I gave you lead 2. And so now you know, okay, if I say lead 2, this is the ion I'm talking about. It's a little bit more of a challenge if I don't give you the name and I give you a formula, because the name of this compound isn't just chromium chloride. You have to tell the reader which chromium ion we're dealing with. And so how do you sort that out? Well, you have to do sort of a reverse cross-down game. And so we write the formulas of the ions down in reverse. The key, the linchpin, the keystone, the thing that helps you solve this is that you do know without a doubt the formula for the chloride ion. That's right, now you're with me. You do know without a doubt the formula for chloride is Cl minus, because of its position on the periodic table. So what this means is that you know that whatever the charge of chloride is, it crossed down. And so if I need 2 chlorides, then that means I have a total of 2 times minus 1. So the total negative charge is 2 minus. I only have 1 chromium, and so whatever the charge on chromium is, it's got to be 2 plus. And so that means that the charge on chromium is by itself 2 plus. And so if I were to say the name of this compound, I would say this is chromium 2 chloride. And that's by far the more challenging situation to deal with. That's by far the most challenging situation to deal with. Let me do just one more example. Let's do, let me look at my periodic table so I can come up with an idea. How about Mn2 O3? What's the name of this compound? So the question that's been asked is chloride minus 1 because it's group 17? Absolutely. That's how we know. When you always will have one thing that's predictable that you can look on the periodic table, figure out its certain 100% all the time charge, and use that to figure out the charge of the thing that you don't know. You don't have to know the charge of every ion in the compound, but you need to know at least the charge of one of them. So here's another example. You're always going to be paired with one ion you know the charge of, or you can get the charge of. And in this case, it's oxide, right? You know oxide is O2 minus. And so this was, again, an example of sort of the reverse cross-down game. What was the charge on manganese then? What's the charge on manganese? It's got to balance out that oxygen. So it's 3 plus, right? So if I have 2 manganese that are 3 plus, I get a total charge of 6 plus. If I have 3 oxides that are 2 minus, then I get a total charge of 6 minus. My net charge is 0. Remember, the whole idea behind this is to get them to be, is that the ionic compound is an overall neutral charge. That is one way that you can do it. You can just flip them like that to determine the charge. And so, yeah, and I just want to make sure that we use absolutely correct. Needs to be in parentheses, manganese. Oops, it's not 2. 3 oxide. Manganese 3 oxide is the name of this compound. Okay, let me show you some problems with this. Where do you get in trouble? The cross-down method will work every time, almost every time, except it gets you into some trouble like this. This would be lead 2 oxide. Another example would be magnesium sulfide. For lead 2 oxide, it's the molecule that comes from the lead 2 ion and oxide. What's the formula? Well, cross down would say, I'm going to cross down that, I'm going to cross down that, and I'm going to write Pb2O2. Is this the formula for lead 2 oxide? Diana doesn't agree with me. Right, and right, you guys go with your classmate here in this case. The formulas for ionic compounds are always represented in their lowest whole number ratio. So if the cross-down method gets you 2 and 2, then you can always reduce that by dividing both of those numbers by 2 and getting 1 and 1. So the lowest whole number ratio is how you express the formula for ionic compounds. And we'll talk about that in a second. It's really always the empirical formula. We'll talk about that in the next section. But this is where the cross-down method, just following it blindly, will get you into some trouble. And so I just want to make sure that we're aware of this instance. So let's do this other example real quick, magnesium sulfide. So the magnesium is something that's predictable. It's Mg2+ when it's an ion, magnesium ion. Sulfide is predictable as well, S2-. So cross-down might get you to say Mg2, S2, but again, that's not the lowest whole number ratio. So the formula for magnesium sulfide is just MgS. This one's going to be a real challenge. What do you think about this one? When I say that magnesium is predictable, what I mean is that magnesium is a group 2 cation, and group 2 cations always have the same charge, so it's always 2+. I guess do you put the 2- next to oxide or the S2-? I don't understand what that means. I put 2- here on oxide because the formula for oxide is O2-. It's in group 16. I put a 2- on sulfide because again, sulfur's in group 16 as well. So I know that the formula for sulfide is S2-. So I did put the 2- next to them because that is their charge. I didn't do it later. You mean down here? Ah, this is a great question. So the question is asked, well, how come I'm not putting the formula of the charges down over here? So I think the question is asked, why am I not doing this? And the reason is it's convention. It's not that magnesium sulfide isn't made from ions that have a charge. It's that by convention, when we write the formula for an ionic compound, we don't include the charges. The reason we don't include the charges is that you don't technically need to show the reader the charges because it is expected that the reader can always sort the charges out from their knowledge, whether or not it's predictable or whether you use a predictable ion to back calculate the charge of one that's not predictable. So this is a great question, and this is a very common mistake. The formula for magnesium sulfide is MgS. If you write Mg 2 plus S 2 minus, you're wrong. So that's not counted correctly. But keep in mind, it is, in reality, a magnesium 2 plus ion interacting with an S2 minus ion. The other question is, are we not supposed to use the Roman numeral for magnesium? And the answer to that is no. We don't use the Roman numeral for magnesium because magnesium is predictable. Magnesium only takes one charge. Remember, we only use Roman numerals for those transition metals and post-transition metals that take on multiple charges. The point of the Roman numerals is to tell the reader which one it is. And again, there'll be 4 exceptions, and I'll write those down in a second. So let's do this one last example before we get to those 4 exceptions. All right, so what do we have here? What's the name of this compound? What's the name of this compound? Let's see what crossdown gets us. Do we know the charge on oxide? Yeah, it's not dioxide. And so don't get confused because we're never going to use di, tri, tetra, whatever when it comes to ionic compounds. We're going to save that for later. Oh, there we go. There we go. It's lead 4 oxide. And let's see how we figured that out. Here's how we figured that out. We know that oxide always has the same charge, O2 minus. How many of them are there? How many are there? I have 2 that have a 2 minus charge, so the total negative charge is -4. I only have 1 lead ion. And so that lead ion must neutralize all of the -4 charge. So it's lead 4 plus. And so if we were to check our work, and try to write the formula using the cross-down method, we would first write PB2O4. But then we would say, okay, that's not the lowest whole number ratio because I can divide both of those by 2. And so I would do that and I would write PbO2. And so now that way, now that we've known, we've checked our work, the lead ion in this case is the lead 4 ion. So the name of the compound is lead 4 oxide. Okay. So here are the 4 transition metals that have only 1 charge. And so you don't need to use Roman numerals with them. It's the cadmium ion, and that's Cd2+, zinc ion, and it's always Zn2+. I gotta look just to make sure I'm doing this right. Cadmium, zinc, nickel. Nickel ion is Ni2+ all the time. And the last one is silver ion, and it's always Ag+. So the 4 transition metal ions that have that take on only a single charge are cadmium, zinc, nickel, and silver ions. They don't have any other charges. Cadmium is always cadmium 2+. Zinc ion is always zinc 2+. Nickel ion is always nickel 2+. And silver ion is always silver plus. So you don't have to use Roman numerals for these. No Roman numerals. They'll always be these charges. We use Roman numerals for transition metals and post-transition metals that can have multiple charges. We have to tell the reader which charge it is. So let's do one more example so that I can sort of address the question, how did we get that 4 again? Well, let's take a look at something else. Let's do cobalt. Let's do this guy. I'm making one up. You'll never see this one. I don't think cobalt actually takes this charge, but we'll see. Actually, let me switch this out to 2. So what's the name of this compound? All right, so this is how we're going to sort it out. So I want to make sure everybody's with me. I'm going to go one last time. I'm going to do it all the way through. And so make sure you're following closely along. We need to figure out the charge on cobalt because cobalt is a transition metal and we don't know. We can't just look at the periodic table and say, it's this. We can figure it out for nitride though. What's the formula for nitride? It's in group 15. And so we know that in group 15, it's 3-. What we need to do is figure out what the charge on this cobalt is. We don't know that. So this is the question here. So what is it? Well, we have to do a little bit of work. We have to think about it. And what we have to think about is that the charge on an ionic compound is overall 0. It's neutral overall in the net sense. And so all plus charge equals all negative charge. And so if we can figure out one, then we can figure out the other. Well, what's the total amount of negative charge that we have? What's the total amount of negative charge that we have in this fictitious compound? It's not 3. It's not 3, right? It's not 3. How many nitrides do we have? We have 2. So then what does that mean? If we have 2 of them, 2 nitrides times, what's the charge on nitride? We figured this out. It's -3. So then what's the total negative charge? -6. So then what does that mean that the total positive charge is? They have to be the same. And so now in order to figure out the charge on the cobalt, we have to say, how many cobalts do I have? I have 1 cobalt times its charge equals +6. Right. So I know the charge on the cobalt is +6. So if I want to write down the name of this compound, it's cobalt 6 nitride. So I hope that helps. I hope that clarifies some of the I don't think so this is what's right. It's 3 minus. I'm not writing this in a compound, so I can write it any way I want to. When I write it in a compound, I always write 3 minus. So I'm hoping that this helps. I hope this helps sort out. I hope this helps sort out how to figure out the charges on these transition metals and post-transition metals so that you can write down the correct names of the compounds. It's easy if you have the charge, right? If I said it's cobalt 5 plus and it's sulfide, then you can just do the cross down game, CO2S5. That's the lowest whole number ratio. You're done. Cobalt is a transition metal, so it takes on multiple charges. It's not one of the exceptions. Remember, the exceptions are nickel 2 plus, silver 1 plus, cadmium 2 plus, and I can't ever without looking at them. Zinc 2 plus. These are the only exceptions. All right, so what I want to do is I want to pause a beat there. So what we've done is let's recall everything we've done with nomenclature. We've done elements, symbols to names, and vice versa. We've done natural formulas and states of elements. Remember that oxygen is O2 gas, etc. This is what we mean by that. We did formulas of monatomic ions and their names. And we did formulas of ionic compounds. Remember, compounds is a vocabulary word. It means 2 different types of elements. And we did their names. We just spent a long time talking about that. The next thing we're going to do is polyatomic ions. And what does polyatomic means? More than 1 atom in an ion. So it's like a molecule that has a charge, is essentially what we're talking about. It's like a molecule that has a charge. And so let's sort this out. Okay. I want to stop this because I want to jump right into the camera and be dramatic. If you don't get this part, you're going to miss so many points on the final exam. In a second, I'm going to tell you why it's important that you study this. When it comes to monatomic ions, you're going to have a periodic table. You're going to be able to sort out the charges. Even with transition metals, I'll always give you something that'll help you figure out the charge. Well, what's up with these polyatomic ions then? Let me give you an example. Polyatomic, more than 1 atom. It's got a nitrogen and 3 oxygens, and they're all bound together. So it's like a molecule. It is a molecule, specifically a compound, but it has a charge. It's a compound with a charge, a polyatomic ion. Here's another one. Here's the name of one. Here's the big deal. Monatomic ions, you have a periodic table. You can look at the periodic table. You can sort out the charge based on its position in the periodic table. Or I'm going to give you some information that'll allow you to sort out the charge. I'll either tell you the name of a transition metal or post-transition metal ion, or I'll give you a compound that has another ion in it, and you can figure out the charge of the post-transition metal or transition metal ion based on that other ion. Here's the deal. How do you figure out and predict the charges of polyatomic ions? How do you figure out and predict the formulas and charges on polyatomic ions? You don't. You just don't. Right. The only option that you have is to brute force memorize them. It's it. Some of you guys are going right now. And that's okay. And I get that. But here's what happens in general chemistry, and yeah, these are the 22 exactly. We're gonna get to the 22. Students get overwhelmed at this point and they put this off. You can't. You have to know them by heart, and you have to know them very quickly. You have to know them just like you know your neighbor's name or your kid's name, your mom's name, your brother and sister's name. You have to be able to do it so fast. And the reason is that we're going to be using the names nitrate, sulfate, sulfide, phosphate, ammonium, and all that stuff. We're going to be using them one right after another really fast, going down the road for the rest of the semester. And you can't pause and say, what's that formula again? Let me look it up. Because we're already going to be working on a problem at that point while you're still going, what's the formula? Now, remember, on the exams that are going to be during the middle of the semester, you're going to get to use your books and your notes. So I'm frankly not going to ask you a whole lot of questions about what's the formula of this, what's the name of that, because that's just something that you'll be able to Google really quickly. So I'll ask you a few just to remind you that you have to know them. But when it comes down to it, you're going to be doing the final exam, and the final exam is going to be monitored and locked down. And so you're not going to have access to your other devices. You're not going to have access to the internet. You're not going to have access to a cheat sheet. So you're going to have to know these by heart. And there's just a lot of questions it's a 60 question final exam. There's just a lot of questions on that 60 question final exam. That's what's the formula of this? What's the name of that? And a lot of them involve polyatomic ions. And so, I hope that I've at least breaking the sad news to you that there's no way around it. You just have to memorize them. Well, what I'll do is I'll try to organize them in a way that helps you memorize them, because there are some patterns, and the patterns are helpful. And so what I'm going to do is I'm going to start off over here in the corner. And in the corner, I'm going to put the ones that don't really fit with the pattern. In this course, there's only one polyatomic cation that you have to know. Does that mean there aren't other polyatomic cations in existence? No, that's not what that means. That just means that I'm only going to test you on one. And so the one polyatomic cation that you must know is NH4+. This is ammonium. Ammonium. By the way, what's the name of NH3? Neutral, no charge. You know this one? This is just an aside. This is not a polyatomic ion. What's the name of this? The polyatomic ion NH4 is ammonium. What do you think the formula NH3 is called? No charge. Yeah, it's not really that. Is this cold? This is not. Yeah, you don't have to take a big leap here. The common household cleaner, the major constituent of Windex. Ammonia. Let me just make sure I'm doing my spelling right here too. Yeah, and I didn't spell this one correctly, so let me just redo that. My favorite pastime is to embarrass myself on YouTube with spelling. And so yeah, this one is ammonia. Ammonia. Settle down there. Settle down there. We'll get to some ionic compounds that involve polyatomic ions in a second. Actually, you brought up the next one. Okay, so these are the polyatomic ions that don't kind of have a pattern, and the pattern all the pattern does is help you memorize. That's all it does, is it helps you memorize them. But that does bring up another one that doesn't fit the pattern that helps you memorize. So I'll just put it up here off to the side. This one is hydroxide. This one is hydroxide. And so someone's in there typing the formula or a name of a compound. What would be the formula for the compound ammonium hydroxide? It would just be that. But we'll get to that in a second. We'll get to that in a second. Let's see. There is one more compound, a polyatomic ion, that you have to know. Acetate. C2H3O2 minus acetate. I want you to notice something about hydroxide. What's different about the way that I've written hydroxide and the way that I wrote all the other two? What's different about it? Yeah, it's really about where I put the charge. There is nothing wrong with this. I write the charge on the minus on the left side in this particular case for reasons that have to do with where the charge actually is located. So you will see me write hydroxide like this quite a bit. They're both correct, but just to be consistent, let me write it down like this for right now. Hydroxide. Yeah. Okay, so there's the three that sort of don't fit the pattern. Let me make sure. Yeah, I don't think there's anything else in there that doesn't fit the pattern. Okay, so let's do this. Nitrate. Sulfate. Phosphate. Carbonate. A lot of eights, and that's great that you're noticing this pattern. 8, 8, 8, 8. And what we call them are 8 ions. So let's continue on with this. Let me let me show you the next set of ions that I want to show you. And the reason I'm going to write them this way should be apparent in a second. NO2 minus is nitrite. SO3, 2 minus, is sulfite. PO4, 3 minus, is phosphite. Here's a trick question. What would be the formula for carbonite? This is a trick question, but what would the formula for carbonite be based on the pattern so far? Oh, I screwed up phosphate, so phosphite. Let me unscrew this up. That should help with the pattern. Now let's re-examine. So phosphite is PO3, 3 minus. Phosphate is PO4, 3 minus. Yeah, and so if we're following the pattern, carbonite would be CO2, 2 minus. What's happening with the number of oxygens each time? 3 goes to 2, 4 goes to 3, 4 goes to 3, 3 goes to 2. What's happening with the charges though? Charges are the same, 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 same. Why is it a trick question though? Yeah, one less oxygen, the same charges. Why is it a trick question though? Carbonite is only in Star Wars. Yeah. Han Solo, frozen in carbonite, right? Carbonite only exists in Star Wars. It's not a real ionic compound. But I wanted you to take a look, or excuse me, it's not a real polyatomic ion. But I wanted you to look at the pattern. Thanks for pointing out phosphite to me because I would have missed that. I wanted you to see the pattern of how the numbers of oxygens change and think about what it would be if it were real, but it's not real. Carbonite is only in Star Wars, so there isn't a carbonite. Okay. So let's do one more. Let me take this, I want to just erase it, and I'm going to move it over just a little bit to get some room. CO3, 2 minus, carbonate. Let's do this one. ClO3 minus and ClO2 minus. This one is CHLOR chlorate. What's this one? Chlorite. Here's the difference though. We're going to have a bunch of these. We're going to have a bunch of these types. I'm going to have a chlorate, a bromate, and an iodate. And the only difference is going to be the halogen that starts the compound. The additional difference is that unlike nitrate, sulfate, phosphate, nitrite, sulfite, phosphite, which are the only versions of those polyatomic ions, there are additional versions of this one and this one. This one is perchlorate. This one is hypoiodite. Perchlorate and hypoiodite. But look at the pattern. The pattern still holds. We're going from 4 to 3 to 2 to 1 oxygens. So as long as you are starting to get your head around sort of knowing these, if you know those 8 ions, and you know we're going to why iodites. Oh, thank you. Man, I'm just really not doing this right. Hypochlorite. Thank you. Thank you. So I apologize again. Thanks for pointing that out. I'm always making writing mistakes. So it's not, I'm going to do iodite in a second, and I'll show you that in a second. There is a hypoiodite, an iodate, and a periodate, and as well as there's a bromine version of that. But what I'm trying to point out at this point is that if you know the 3 at the top that you don't really have a pattern with them, and you kind of know this set, then you can build the rest of them by remembering that all that changes is the suffix "ite" and the number of oxygens. That's the only thing that changes. Okay, and so let me show you the other ones. And so I'm just going to move these over just a little bit, shrink them down. Actually, I'm going to go ahead and move them over. Just like I have a chlorate, I have a BrO3 minus, a BrO2 minus, a BrO minus, and a BrO4 minus. I have an IO4 minus, an IO3 minus, an IO2 minus, and an IO minus. This is bromate and bromite. This is iodate and iodite. This is perbromate. This is periodate. This is hypobromite. And this is hypoiodate. You forgot L, I think. Or did I forget an L? I don't see an L. Iodite, iodate, periodate. I'm not sure where someone's suggesting that I forgot an L. I'm not sure where I'm missing an L. Chlorates, chlorite, perchlorate. I was before, okay. All right, I fixed it. Good. All right, cool. So again, if you just think about those first set of 8 ions, then you can really build all of this other stuff. My suggestion to you, so let's see, how many is this? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I don't think I can go backwards, but there were 1, 2, 3 up here. There was 1, there was 4, 5, 6, 7, 8, 9, 10, nothing here. So there was 10 plus 12. There's my 22. So that's all 22 of them. And so let me show you what I suggest that you do. And this is just a study method. Get yourself an index card. Get yourself an index card. or piece of paper, whatever you want to do. And do this. On the front, have the formula. And on the back, have the name. And that way you can quiz yourself either direction. So if you look at the back of the card, you see the word nitrate, you use the word nitrate to come up with the formula NO3-. If you see the front of the card, NO3-, what you want to try to do is come up with the name, nitrate. And so what I'm going to do is I'm going to leave it there because that's quite a bit of stuff to do. And so you have a lot of work to do this weekend. Yeah, flashcards. So my suggestion to you is spend the weekend learning the names and formulas of these 22. If that's all you do this weekend, do that. You have to know the formula and the name. You have to be able to go back and forth. If I give you the formula, you have to tell me the name. If I give you the name, you have to tell me the formula. And this is true with all nomenclature, right? Even with the basic thing like oxygen atom, right? You have to be able to go O. Or if I go PB, you have to be able to go lead. It's even in the very basic, that's what we're doing. Formulas to names, names to formulas. So I'm going to stop right there.